Unit Operation Classroom. Today we are going to discuss determination of capillary tube diameter. We'll look into it. What is a capillary tube and how to determine its diameter from capillary rise method. Okay. First, let's read the problem definition. My name is Shekhar Bhattacharjee. When a cylindrical capillary glass tube, open at both ends, is vertically inserted in a pool of water, the water level in the tube rises to 7 centimeter relative to the water level outside the tube. So let's say this is my let's say beaker full of water here. So when we put a capillary tube into it, so what happens? The water rises and it forms a meniscus like this, a concave meniscus. It forms a concave meniscus for glass and water. And this height in this particular case is 7 centimeter. That's what it says. Okay. So the values of surface tension is given. The contact angle is 0 degree. So we're looking to see what is the contact angle and what happens if it's a 0 degree. The density of water, of course, is this, we know, and the acceleration due to gravity g is given. So from this data, we have to determine the diameter of the capillary tube. So we have to determine the diameter of this capillary tube from this particular small experiment. And then we will see what are the applications of this particular concept in chemical engineering. So what are the key concepts here? First of all, we know that the capillary rise is caused by the surface tension with the glass tube, contact angles and weighting of glass surface. What is that particular thing? How the contact angles is related to the weighting of the glass surface, and how to use the force balance between the surface tension force and the weight of the column of liquid. So let's look into the physics of this rise of water, or in case of mercury. In case of mercury, what happens? Let's say if it is a mercury, what happens if you dip a capillary tube into it? So basically, what happens? It forms a convex meniscus, and there's a dip. In this case, there's a liquid rises up, and in this case, the level of mercury goes down. So anyway, for this particular problem, what is the underlying concept? The vertical component of the surface tension lifts water upward until it is exactly balanced by the water weight of raised water column. What does it mean? Um, let's expand this one here. So as you can see, this is by the meniscus, this concave meniscus here. So there's also continuous weighting. If you think of this, the tube, so there's a continuous weighting of this entire surface here. And so this is my contact angle here, and it is always just measured to the liquid, in this case, water. So if this is the contact angle, this is the tangent at this liquid air or water air interface and the glass tube. So this is my angle theta here. Of course, the theta is saying 0, so we look into it, but we are making it general. If this angle is theta, of course, this angle also would be theta. So if that's the surface tension force here, then there'll be two. It can be split into two components. One is a vertical force, and the other is a horizontal force. Let's look at the vertical force here. So this vertical force. So this is the tube. Tube surface on which every point this vertical force acts here. So if this is sigma, so this will be sigma sine theta, and this will be sigma cos theta. So this sigma cos theta is working along the periphery, along the perimeter of this tube here. So this is pi d. So this is my pi d, and the vertical force is sigma cos theta. So the entire force which is working on this to lift it up, the vertical force is pi d sigma cos theta. And at equilibrium, the weight of the water column is balanced exactly by this surface tension force. That means this water level will rise up to only that particular point at which the surface tension vertical component of the surface tension force balances the weight of the liquid. So we have looked at this is the vertical component surface tension force. What is the weight of the liquid? That part is of course easy. This is pi r square or pi d square over 4. Pi square 4 times of course h. That's a volume here. No, not that one. That's a volume here. That's the volume of the liquid multiplied by rho g. Right. So at equilibrium, we can say this is pi d, this surface tension, particle component surface tension force is the weight. So if we do that, if we do the math, so this is the equation. That's what we're going to use. Okay. Now, in our particular case, it says the angle theta is equal to 0. That means it basically completely wetting the surface of the tube. If the contact angle becomes 0, we look into it. So it's a complete wetting of the glass surface. So this theta is given as 0, and this value of sigma is given, this rho is given, g is given. So automatically we can calculate the value of A, we can calculate the value of D, since the value of H is given, which is 7 centimeter. So we put this equation here. So we have just shown this calculation. All the details are given in this website. So this is basically 400 micrometer. All right. So just a couple of important notes. If the liquid wets the surface, as for example, water on glass, theta is less than 90 degree. Of course, cos theta will be greater than 0. So there'll be a capillary rise, which is happening in this case as the liquid goes up. For our case, of course, theta is equal to 0 degree. That means it's a complete wetting of the surface. Okay. If the liquid does not wet, as for a simple mercury in glass, we know it does not wet at all, then this contact angle is greater than 90 degrees. So, of course, cosine theta will be less than 0, and there's a capillary depression. Of the capillary depression. So basically, as I said, so if you insert a tube, so let's say this is mercury, so this and this is a convex meniscus. So we can see from this equation here, this rise and the diameter are inversely proportional. Rise is inversely proportional to the radius. So smaller, narrower the tube, higher the rise. So narrower the tube, so the narrower if it is rise, so that we higher the rise of the water. Okay. So these are very simple, and this physics has been done even in high school classes also. What is interesting here is let's look at the practical application of this problem, that is capillary rise for chemical engineers. So, we use a lot of packed bed reactors, fluidized bed reactors, trickle blend reactors, slurry reactors, etc., for different types of conversion of different types of chemical products. Wetting of the catalyst particles, that's a very important issue, because so there are intricate number of pores, large number of pores inside each catalyst particle. I'm just showing an enlarged portion of that. And so this wetting of this the liquid in case of liquid phase reaction is very important for effective reaction inside the pores, right? So how the surface tension becomes important here? Liquid enters the catalyst particles by wetting and capillary action. So these are very small pores. So of course the liquid enters by the capillary action, and that is of course related to the wetting. And this wetting information is of course given over here. This is directly can be obtained from, or can be inferred from, or can be guessed from the contact angle. Okay, which depends upon the liquid and the material. Pore penetration affects intraparticle mass transfer, which is of course pore penetration. So that is of course we know is very important for intraparticle mass transfer. That means mass transfer within the catalyst pores, to reach the active sites. And poor weighting reduces catalyst effectiveness factor and overall reaction rate. So as you can see, the surface tension or the entry of the liquid through capillary action, as we have seen here, has a direct application in chemical engineering applications. Capillary action controls moisture migration through pores and therefore influences drying rate of porous solids. Okay. Wetting of filter media, again, there are a lot of pores in filter media and filter cakes, affect liquid penetration and the filtration rate. Contact angle and surface tension are important for solvent absorption, coating uniformity, and weighting of fibrous materials. Uh, One important thing, that small pore or tube diameter, of course, that is automatically related to stronger capillary rise. Smaller the pore size, of course, there will be stronger capillary rise and stronger liquid penetration into the pores that comes inside the catalyst particle. So that's a very important one. Anyway, so finally, this 400 micron or 400 micrometer is the answer to this problem. So this is 400 micrometer.